Hello everybody. We're still talking about the options in plotting or displaying the outputs of the solution of the partial differential equation in Matlab partial differential equation toolbox. And we are exploring now these two options, which are the deformant mesh and the high 3D plot. If we do the deformant mesh and we do the plotting, you'd see that the plot looks very weird. And it's like the original area was a rectangular area that we had, and there is a shrinkage in the sides with low concentration and like a swelling in the areas that have high concentration. And this is kind of what the deformant mesh does. It changes the area based on the concentration, but this is not the easiest way to understand it. So to understand it, let's put it as the height in 3D plot, and I'll make it first as a concentration gradient, like the same option that we had here. And if we plot it, there is a new plot that will open up here, and this plot, like what we see, is a 3D plot where it shows the dimensions as x and y. So if you look at it from the top, it's gonna be like this. This is the 16 by 20. This is the dimensions. This is the shape that we have. But in 3D plot, it is the height represents the gradient of c. And we have the vector fields here in the bottom to show the direction of flow, but this is what we have. You'd see here the height represents the flux, so you would have the minimum height at almost 0 at the center, and for the corners, the four corners, I have these maximum values of the flux, and the flux decreases from here to here, or the gradient, or the concentration gradient. Yeah, it's the same. So it decreases to the center. So this height represents the flux. So it's like you have the concentration as colors, you have the flux as arrows, and you have the magnitude of the flux or the concentration gradient as a height. So this is kind of nice representation of the of all the parameters that we have in a 3D plot. Let's take a look at the concentration. It's gonna be nice to see the concentration. We can make the deformed mesh for its only concentration gradient. There is no option for concentration because this is a vector. But if you do the deformed mesh as let's show the mesh, it's gonna look better. So if you want to take a look at the concentration distribution, and this is the same thing. You have the minimum concentration at the edges on the sides, and the concentration increases, and this is how the concentration profile looks like. So it's a very nice way of taking a look at the profile. So the deformed mesh is just one of the ways that we can look at it. So it shows everything in 2Ds, not in 3Ds. So it's showing the same thing here, that instead of having it as a height, the height is represented as an increase in the area for the big values and decrease in the areas for the small values. So this is the height in 3D plot, and this is the deformed mesh. There are two nice options that we can show as well. The last thing that we will discuss here is the exportation of the data. So let's say I want to get the data. So all the outputs that I have seen till now are just images, 3D plots, and no numbers. I don't have any numbers except for the maximum, the minimum for the scale that I have to this right. So if I want to export the data, to see the data as numbers, we can export them from after the solution, of course. From here you have the option to export the mesh. So if in this mesh here, you can export mesh, and exports the mesh as PET. P is points, E is edges, and T is triangles. So I'll press OK. nothing happened here, but let's do one more thing. I can export the solution as well, which is U. It calls the concentration U. So I'm gonna call it U. You can call it C, whatever the value that you want. So now you have the data exported, and of course they are exported to Matlab, and you'll have the outputs here. From the look at the dimensions of these outputs that we have here, you would see that the or let's do one thing first, which is going back to the mesh mode, and in the mesh we can show the nodes label, we can show the triangles label. It's not gonna be easy to see here, but let's take a look. We'll see we have here, we said that the maximum number of triangles is in the middle, so it's 1,000 and something, if I'm not wrong. I see the maximum here is 1,060 something. So here for the triangles it's 1,072, so it's 1,000. This is the number of triangles, and of course the number of edges is much better, and the number of nodes is I mean the number of nodes is less. I'm sorry, it's less than the number of number of triangles, because they're common between many triangles. So you'll have one node here, it's common between 5 or 6 triangles, so the number of nodes is less. Of course, if they're separate triangles, it would be more, but for this case, it's almost half the number of triangles. This is the number of points, and the edges is 72 edges. Again, because they're common between triangles. So what you see here is that the number that you have here for the concentration is 573 multiplied by 1, which is 573 rows and 1 column, and for the points you have 2 multiplied by 573, and this is the corners or the nodes that we have. So the concentration is calculated at the nodes, so this is why I can relate from the numbers. In the point, you would see that each point is represented by 2 numbers, which is the coordinates, x and y coordinates. So I have 518. This is number 1, it's 518, and this is number 2, it's 2518, and then 252, and then 52. So this is the x coordinates, and this is the y coordinates, and this is the concentration at each of these coordinates, at each of these points. So you'd see for the 4 corners it's 0.0505, which is the average between the maximum and the minimum, because it's the exact corner, the point of intersection between the 2 sides. So you can use these as the coordinates of each point and the concentration at this point. So x and y and the concentration that is at this point, which is actually what we have at this or the output that we get at this. So what the software does is it calculates the concentration at each of these nodes. So if you're interested in the concentration of this surface or this side, then, or the profile, the flux, any kind of information at specific side, you can get the points that you want, and then you can get the output from you. So it's gonna be tricky to pick the right values within this like big number of numbers, especially if you have big geometry, or you have very refined mesh, then it's gonna be tough to pick the actual or the right points, but it's doable. So once you have the numbers, you can play with them, you can do anything that you want. So this is how we solve the problem. I'm gonna do one more thing here, which I mentioned earlier, which is the solution of this system based on the symmetry boundary condition, and we will compare this to what we have, and we will see this in the next video. So I'll see you then, inshallah. Goodbye.